All right, let's look at this example, and then we can learn about some symmetry arguments we can make to make our job easier. This shape has a name as well. It's called a four-leaved rose, and we will see why. The radius changes as cosine of 2 theta. Cosine 2 theta means that now between 0 and 2 pi, you actually have two complete cosine graphs. And why is that? Well, because the time period of this function is pi. And why do we consider till 2 pi? Because in our polar coordinate system, theta goes from 0 to 2 pi. So we have to consider one full rotation. So let's mark some of these points that are important. Pi over 4, pi over 2, 3 pi over 4 pi, then pi plus pi over 4 is 5 pi over 4, 3 pi over 2, 7 pi over 4, and finally 8 pi over 4, which is 2 pi. Now on the axis, this is 0 and 2 pi, and this is pi over 2, this is pi, this is 3 pi over 2. Now pi over 4 is halfway, right? So pi over 4 is the line y equals x. Similarly, if you extend this over here, that's going to be halfway between these, which is 5 pi over 4. This angle is going to be 3 pi over 4, and when extended to the fourth quadrant, it's halfway between these, which is 7 pi over 4. And I notice that at these multiples of pi over 4, it becomes 0, so my radius is 0. So which means along each of these, or at each of these dotted points, I come back to the origin because r is 0. Okay, where do I start? The amplitude is 1. So I start, when my angle is 0, I start at a point on here where r is 1. Maybe let's use red, more visible. R equals 1, I start here. What happens when I go from 0 to pi over 4? My distance is decreasing and becomes 0. So starting here, I am moving towards the origin. And at exactly pi over 4, I become 0. From pi over 4 to pi over 2, I increase. I increase and I become 1 again. From pi over 2 to 3 pi over 4, I decrease and I come back to 0. And the same behavior is repeated. Now from 3 pi over 4 to pi, I increase and I go up to 1. Then I decrease and I come back to 0. Same way, I increase and I go up to 1. I decrease and I come back to 0. I increase and I go back to 1. So it's not symmetric. All four petals should be of the same size. But essentially, what is happening here is you're getting a shape which is called a four-leaved rose. Now you notice certain symmetries here, right? If you take this line, top of this line is the same as the bottom. If you look at the x-axis, the top and bottom are the same. You look at the y-axis, the left and right are the same. So there's a lot of symmetry stuff going on over here, which is going to be our goal, to look at what possible symmetric structures can I extract, or information can I extract, so that my graph making process becomes slightly easier. So in rectangular coordinates, we have these certain symmetries, like replacing x by negative x, or taking the negative of the function If they remain the same, then it tells us, for example, the function looks the same if reflected along x-axis, or reflected along y-axis, or reflected along y equals x, and all of that. So there are three types of symmetry that we notice here. First of all, you take your equation and you replace the angle by the negative angle, and if the equation is unchanged. Example, r equals cosine theta, right? Because cosine of negative theta is the same as cosine theta. Then you would have a symmetry along the polar axis, meaning for any point r theta, the point r negative theta would also be in the graph. So this would look like that. So sort of also you can think of it as symmetry along the x-axis. The second one is, if I replace r by negative r and I replace theta by theta plus pi, and everything remains unchanged. This means that the point r theta and the point negative r, theta plus pi, so it's exactly 180 degree apart, are the same. This will give me sort of this loopy structure, having a symmetry which is called symmetry about the pole. Pole meaning this origin right here in this case. Now what would be an example of this? If I want equation to be unchanged when I change r to negative r, one way to make sure that happens is to have an r squared term. If I want theta and theta plus pi to give me the same answer, then what I really want is anything going from here to here having the same sign. That sort of happens for tangent theta. So r square equals, maybe a tan theta would be an example of where we have this sort of symmetry. And the last kind of symmetry is, you let r be and you replace angle theta by pi minus theta. When you do that, you get symmetry about pi over 2. Now where is pi over 2? Pi over 2 is the y-axis. So this looks like a symmetry around y-axis. Where would that happen? Let's see. So sine would be a good example. So something like r sine theta would have that sort of symmetry. Okay, let's use symmetry to graph this particular function, which is given r equals 1 plus 2 cosine theta. First of all, clear observation, changing r to negative r, not valid because that changes everything. Changing theta to negative theta, it all remains the same. So that's good. It means it has symmetry about the polar axis, meaning whatever is on top is going to be the same as that in the bottom. So we know that. Now we go ahead with our regular analysis of 1 plus 2 cosine theta. 1 plus 2 cosine theta in 0 to 2 pi. So 2 cosine theta goes from negative 2 to 2. Adding 1 makes it 0 someplace, but it still becomes negative 1 somewhere. So it starts at 3, becomes 0, becomes negative 1, and ends up at 3. Now it's important for us to find what these points are. To do that, we're going to solve 1 plus 2 cosine theta equals 0. So cosine theta equals negative half, which we know how to solve. It's going to come out to 2 pi over 3 and 4 pi over 3. So this point is 2 pi over 3 and this point is 4 pi over 3. And this here is exactly halfway, which is pi. Now let me color this red and the rest black. So my argument says that it's going to be symmetric. So I can just look at what happens between 0 and pi and then just flip it and take a reflection. So let's do exactly that. 0, my radius is 3. I start here. And then at some 2 pi over 3, I become 0. Now where is this 2 pi over 3? That's 120 degrees. So that's right here. Theta is 2 pi over 3. So I only become 0 all the way here. And then what happens? From there onwards to pi, I sort of increase again to get to 1. So that's what it looks like from 0 to pi. And my symmetry argument says that, well, the other half of this is just going to be a copy of it, where this here, that's exactly going to be 4 pi over 3, which is when it becomes 0 again. So this is an interesting shape. It intersects with itself, right? Self-intersecting shape. And this shape actually has a name, Limaçon or Limaçon, I don't know. It's a French word for snail. So using symmetry argument, what we get as a result of that is that you can basically just look at halfway through, and you can take reflections to get the final curve. Okay, the next example is family of curves. So I'm going to stop this video here and then do this particular exploration in the next video.